Now, continuing on, we're trying to find what the alpha and beta are, and the value of little j, the eigenvalues of the total angular momentum, big J. Right? Try to find those. Try to find those values. So I've been setting up tools for you to be able to do that. Now, I mean, if you just look at this sort of stuff, it gets quite complicated. I put homework ? If you can actually do all this stuff, I take my hat off to you. It's not easy. It's more a case of that detested phrase amongst mathematical physicists, and certainly amongst pure mathematicians, ICBST. It can be shown that. In other words, you're not going to be shown it, you're just going to have it thrown at you, and you just sort of have to accept it. So it's a bit like that here. But if you care to really plunge into it and try to solve it, take it as a challenge. If you're a true author, maybe you will relish the challenge. Okay, so some of the tools that we were using, we have the ladder operators for the L operator, L plus L minus, defined as Lx plus or minus I Ly. We know from earlier chapters we have an expression in terms of the polar angles theta and phi for Lx hat. Here's the equivalent one here for Ly hat. Here's your operator in terms of phis and thetas, the polar angles. Okay. We also, from earlier chapters, we also know the eigenfunctions and the normalization factor for L. Actually, I should put, that shouldn't be psi, that should be y. It's the, that y. They're the spherical, what's the term? Harmonics, yeah, spherical harmonics. So for angular momentum, the eigenfunction for Ln, so these are two quantum numbers, L being the particular value for the angular momentum, orbital angular momentum, M, as usual, the component of L along the z-axis. So that's in the quantum number Dirac notation, the ket form, 3 bars. So here's your spherical harmonic. So these are your eigenstates of your angular momentum problem. Now remember, we found an expression for the spherical harmonics, the y LMs, and they were the, oh gosh, there's so many polynomials. Which one was that? Legendre? Yeah. So this is the associated Legendre polynomial, right? And this came from the psi part. That was your eigenfunction for the z component. Anyway, so this product, so this is the polar part, and this is, the theta part, this is the phi part of your spherical harmonic, and this was just a normalization constant. Right? So you've seen this before. Okay, so you plug that in to make this normalizable. So you get a normalized expression. All right, now. So you start with all these tools, all these prerequisites, and here's the challenge. You need to show that the raising and lowering operator of L gives you this expression, which is So good luck if you care to try that, right? So the textbook certainly doesn't go through the details of how it's done. So that's why I put a sort of somewhat cynical question mark, exclamation mark comment to the homework. So good luck with it if you want to try it, right? So we're left with these expressions. All right. Now what? So we have an expression for the raising and lowering operator for L hat acting on this eigenstate Lm. All right, and we're going to use that. We'll use this in a moment. So keep that in mind. All right. Now back to our. So that's a sort of stepping stone, like a lemma, a preliminary result that we'll need in a later proof. Well, in this case, calculation. We're now trying to find alpha and beta, these two Clebsch coefficients, or just probability amplitudes like C1, C2. All right. Now remember from previous session we had two relationships: the coupled and uncoupled. We had two sets of mutually commuting operators. Okay. Now we can get a relationship between those two by the following trick, mathematical trick. Remember we had this. We considered this to be like a general eigenfunction, and we expressed it in terms of the alpha beta equation, which you can't see, but it was the equation that I ID'd with a star circle. And I mentioned that I'd be referring to it again in the future. Well, future's now, right? So we can form a relation between these two representations. We can get an equation out of it, which will help us solve. We'll get two equations, which will help us solve for A and B, alpha beta, and J, little j. Okay, now from two sessions back, we had this expression. This is what we wanted, remember? We wanted J hat squared, gave us, well, this is an eigenequation, and we want the eigenvalue to be J into J plus 1, right? So that's one equation. So remember that, okay? Now, remember from the circle star equation, I'll just call it the alpha beta equation from the previous session. Now, on the left-hand side of that alpha beta equation, we had this, Jn, right? And on the right-hand side, we had the alpha something something plus beta something something, okay? Well, look. So if we take the right-hand side of that alpha beta equation, and on the left-hand side of it, it's going to be complicated. So on the left-hand side of the right-hand side of the alpha beta equation, let's multiply by J hat squared. Okay. So we'll have J hat squared into alpha something something plus beta something something, right? But that's the same thing as this, right? J plus 1 h bar squared Jm. Right? So we just equate J squared into alpha something plus beta something. We equate that to this, right? So that gives us then a relation between alpha and beta and J. So on the left-hand side of this new equation, we've got these J's and this eigenstate Jm, and on the right hand side of this new equation, we have j squared times alpha something plus beta something. Right? I hope you're following all this. Okay, but j squared from it's down here. Yeah. So now from the previous session, we had an expression for j squared. It was L hat squared plus S hat squared plus this. Now, I asked you to do for homework. Now remember, towards the end of the previous session, we were talking about L hat plus and L hat minus. Now's where it becomes relevant. This expression here, 2L dot S, like a scalar product, that's just shorthand for Lx hat times Sx hat plus Ly hat times Sy hat plus Lz hat times Sz hat. Okay. Now, show that this expression here equals this. In other words, show that 2ls is equal to 2l's, well, this. Okay, it's pretty easy. It's not obvious where